Hi everyone, this is Srihari Ravishankar along with my teammates Prakriti Girish and Manoj Kumar Palmer. Today we will be presenting our project titled Storage Efficient Branch Target Buffer Design using BTBX with Adaptive Replacement Policies. This work is carried out as a part of ECEN 676 Advanced Computer Architecture project. The primary goal of this project is to improve the efficiency of the branch target buffer, which is a critical component of our processor frontend. Also, as an extension of this work, we explore how BTBX improves storage efficiency and how adaptive replacement policies influence the overall performance and how the results are varying when the storage capacity is increased and decreased for the BTBX, which will be discussed in the upcoming slides. Today, in the modern server applications, we have extremely large instruction footprints, often spanning multiple megabytes. This creates a significant pressure on the front-end structure, such as instruction cache and the BTB. When a BTB miss occurs, the processor must stall, flush, and refetch the instructions, which introduce multi-cycle stalls and reduces the performance. To mitigate this, the designers increase the BTB size. But increasing the size alone is not sufficient. The real issue lies in how efficiently this storage is utilized within each BTB entry. A key inefficiency and the drawback in the conventional BTB is the storage of the full 46-bit target address for every branch, irrespective of the target location. However, the analysis shows that this is unnecessary for most of the branches, since almost like 54% of the branch requires only 6 bits or fewer, and nearly 99% can be represented within 25 bits. This clearly indicates that most branches are short range. Therefore, storing the full target address leads to a significant redundancy and wasted storage, which reduces the number of entries that can be stored and which increases the miss rates. To address this inefficiency, earlier designs such as reduced BTB attempt to eliminate the redundancy by separating the page level information. In this approach, the main BTB stores a pointer and an offset, while the full page number is stored separately. More advanced designs like PDD further extends this idea by introducing multiple structures such as main BTB, page BTB, and region BTB. These designs reduce the duplication of address components, but they still rely on fixed size representations, which limits their efficiency. Despite these improvements, the prior designs introduce several limitations. Firstly, they suffer from indirection penalties, as multiple dependent lookups are required to construct the target address, increasing latency and sometimes causing multi-cycle access. Secondly, they require associative searches in structures like page BTB, region BTB, which increases the power consumption and hardware complexity. Third, they provide poor utilization because they support only limited entry types and cannot efficiently represent a wide range of offset sizes. These limitations help us in motivating to design the BTBX design.
Hi all, I am Manoj and I will be explaining methodologies and implementation. BTPX addresses these issues by storing the offset between the branch program counter and the target instead of storing the full target address. Since most offsets are small, this significantly reduces the number of bits required per entry. However, offsets are not uniform in size, which makes a single fixed width field inefficient. To solve this, BTBX uses a heterogeneous structure where each way stores a different offset size, allowing flexible and efficient storage allocation. In BTBX, the 0-bit way is reserved for return instructions. In this case, the target is not stored in the BTB but is instead obtained from the return address stack. For branches with offsets larger than 25 bits, a separate structure called BTB-XC is used to store full target addresses. Since such branches are rare, This structure remains small and does not impact overall storage efficiency. This design ensures that common cases are optimized while still supporting edge cases. In our implementation, PTBX is modeled using multiple partitions, where each partition corresponds to one offset size. Each partition is direct mapped and together they form a logical set that behaves like a 8-way set associative BTB. This structure simplifies implementation while preserving the benefit of associativity. Additionally, BTB-XC is implemented as a small separate partition to handle large offset branches. The key contribution of our project is extending BTB-X to support adaptive replacement policies. In the original design, LRU is used as a replacement policy. In our work, we decouple the replacement logic from the BTB structure and implement multiple policies including LRU, SRRIP, DRRIP, and SHIP. This allows us to study how different replacement strategies behaves under the same BTB-X architecture. To isolate the effect of BTB policies, we keep the LLC replacement policy fixed. For evaluation, we use the ChamSim trace-driven simulator which models processor behavior under realistic workloads. Each benchmark is executed with a fixed instruction window of 50 million instructions to ensure consistency. We use three key metrics for evaluation. IPC measures overall processor performance. BTB MPKI measures the number of BTB writes per thousand instructions. Finally, we analyze branch offset distribution to validate the assumption that most branches are short range.
I'm Prakriti and I'll be talking about the results that we got as of now. So we start by comparing the conventional BTB and the BTB-X at a fixed storage budget of 14.5 KB. So in the conventional BTB, each entry stores a full 46 to 48-bit target address, which limits the number of entries that can be stored. Because of this limited capacity, we observe high MPKI values, especially in the server workloads with large branch working sets. In contrast, BTB-X stores PC relative offsets instead of full targets and uses the heterogeneous ways to match the actual offset size. This significantly increases the number of effective entries within the same storage budget. As a result, the MPKI reduces by 60 to 70% in the server workloads. For example, in the server 30, we can see that the value drops around from 57 to 17 and server 32 from 62 to 16. This directly translates into performance improvement. IPC increases of about 0.77 to around 0.84, giving an overall improvement of about 8 to 10%. This improvement is even higher in the larger server workloads, sometimes exceeding 20%, because these workloads benefit the most from increased BTB capacity. So the key takeaway here is that BTB-X improves the performance primarily by improving the storage efficiency and increasing effective capacity. To understand why BTB-X is effective, we analyzed the distribution of branch target offsets using diff bits. So we observed that around 55 to 60% of the branches requires lesser than or equal to 6 bits, and around 80 to 85% of the branches requires only lesser than 11 bits, and almost 99 to 99.8% of the branches fit within the 25 bits. So this clearly shows that most branches are short range, meaning their targets are very close to the branch PC. However, the conventional BTB still allocates full 46-bit storage for every branch, which leads to significant storage waste. BTB addresses this by storing only the required number of bits per branch using variable sized ways, which allows many more entries to be stored. This explains why we saw such a large reduction in MPKI in the previous slide. So this distribution validates the core assumption that we made, that BTBX, and this explains how the performance gain is obtained of BTBX based on the target offsets. Now, at the same time, 14.5 KB size, we also evaluate how it performs under different replacement policies. We have taken the cases where the results of about LRU, SRRIP, DRRIP, and SHIP. We observe that LRU gives the best overall IPC trend across most benchmarks, especially client workloads. This is because many programs are loop dominated, where recently used branches are accessed again quickly. LRU captures this behavior effectively. However, in some server workloads like Server 30, Server 32, and Server 27, we see that SRRIP and DRRIP perform slightly better. These workloads have longer reuse distances, meaning branches are not reused immediately. In such cases, LRU may evict useful entries too early, while RRIP-based policies retain them using reuse prediction. Even then, the improvements from SRRIP and DRRIP are very small, around 0.2 to 0.5% IPC, and MPKI differences are also marginal. So the key takeaway we can take from here is that LRU works the best for short reuse, loop-based workloads. RRIP works better for long reuse, server-style workloads. But overall, the replacement policy impact is small compared to the structural improvements that we saw from the previous slide. Next, we study how the behavior changes when we scale the BTB size. At a very small size of 0.9 KB, the BTB is highly constrained. MPKI is very high, around 42 to 46, and only recently used entries survive. So the LRU is the policy that performs the best. At 14.5 KB size, we can see that it has reached a balanced region. The MPKI drops significantly and a reasonable portion of the working set fits. Here, the policy difference becomes visible with RRIP helping in some server workloads. At the large size of 58 KB, MPKI drops to around 0.1. Almost all the branches fit in the BTB. So all policies converge and the replacement decisions have negligible impact. So the trend is very clear. As the capacity increases, we can see that MPKI values decreases. As the capacity increases, the policy importance also decreases. Putting everything together, we can tell that the primary performance improvements comes from the BTBX storage efficient design, which increases the effective capacity by using the offset-based encoding. This leads to the large MPKI reductions and significant IPC improvements, especially in the server workloads. Replacement policies play the secondary role. LRU is the best for loop-heavy, short reuse workloads. SRRIP and DRRIP are better for long reuse patterns in server workloads. However, their overall impact is small compared to the capacity improvements. Finally, as the BTB size increases, the capacity becomes the dominant factor and policy differences almost disappear. So the key takeaway here is that optimizing how we store the branch targets gives us much larger benefits than optimizing how we replace them. In conclusion, we can say that here we conducted this project where we implemented the idea of the project as well as extended it to multiple other replacement policies. And we can see that the BTBX significantly improves the performance by using the efficient offset-based encoding, which increases the effective BTB capacity. This leads to substantial reductions in the MPKI and improvements in the IPC, especially in the server workloads. Replacement policies provide workload-dependent benefits, with LRU performing well for loop-heavy workloads and RRIP-based policies performing better for server workloads. However, their impact is relatively small compared to the benefits of the improved storage design. These are the references, and